The canyon on Mars opens like a wound across a red world, deeper than any trench on Earth and long enough to swallow nations. Its walls show bands of rust, basalt, and ash, each layer a thin sentence in a book that forgot the last chapter. On the horizon, a volcano rises so wide that its edge vanishes into the curve of the planet, a dark table pressed against thin sunlight. Above it all, small machines drift and listen, their antennae counting particles that leave, their cameras stitching a skin for a world that is still taking shape in our minds. We expected tidy clockwork. We found a stage where the props do not behave. Far beyond the orbit of Saturn, a blue-green giant turns like a top that will not steady. The planet's spin is nearly sideways. Its magnetic compass is crazier still, tilted far from the spin, a crown that cannot sit straight. Curtains of aurora appear when that crooked shield aligns just so with the breath of the sun, then fade when the angle slips. The sky of that world seems to open and close, not with seasons alone, but with geometry. Does a planet have a switch? What kind of interior builds a field that leans so far from the body that makes it closer to the frost line? A small body loops through the outer lanes against the traffic. Its orbit cuts across the usual planes as if it heard a different drum. Another object echoes it with a tilt that should have been rare. Then another joins, a little clan of sideways runners at the edge. Is this a signature of mass we cannot see? Or is it our hunger for patterns drawing lines through a sparse sketch? If the rules of a system are sound, why do the exceptions line up so well that they look like a message? We will walk the scar fields of Mars, where one hemisphere is a quilt of old craters and highlands, and the other is a plain that looks almost young, low, and smooth. One planet, two biographies, stitched along a jagged seam you could trace with your hand. Along that seam, a world-sized canyon dives so far that noon becomes a dim hallway. Wind piles dust into the sky, and noon turns to copper. Rocks that should have fallen crumble into talus, then into powder. Then they float for hours because the air is not heavy enough to make them hurry back. The planet breathes, then fails to keep its breath. We will look in ultraviolet and in the energy of charged particles, where a thin atmosphere glows like a ghost around red stone. At the day side, the stream from the sun pushes against the planet's gases, and the high stuff peels away along lines the eye cannot see. Sensors count ions as they go. A few stolen molecules per second becomes a river across ages, and a river becomes an absent ocean. We used to imagine that a world loses air in single disasters, in shocks that write endings. Here loss is a habit measured by a patient instrument, and patience can move mountains the way frost does. We turn our heads back to the tilted giant. There, a magnetosphere warps so strangely that the boundary between star weather and planetary weather swings like a door on an odd hinge. When the hinge lines up, charged particles pour in and light the poles. When it slips, the curtain closes. It is not a failure of physics. It is an invitation. A switch implies a circuit. A circuit implies a deeper layout in the layers we will never drill. At the storm city of the biggest planet, moons write their own arguments. One bleeds lava into black vacuum, its surface young and angry. One is ice to its core, yet it breathes vapor through cracks that vent into space and freeze into delicate fans. One, rare among moons, makes a shield of its own, a miniature magnetosphere wrapped around a body that should have been passive. Heat and cold argue, and chemistry listens. If there is a recipe for complexity, it may be a slow negotiation between fire and brine, between tides and rock, under lids that do not let light in. Then the rebel orbits return to the stage. They are not alone, not random, not easy to dismiss. Their tilts, their directions, their gentle synchronies whisper about a shepherd that stays off camera. Are we learning to hear the bass line of the outer system? Or are we teasing faces from a cloud? How do you test a rumor written in ellipses? You add time. You build surveys that do not flinch. You write your priors on the board, and you agree to erase them if the next round of data asks you to. All of this would be trivia if it did not line up. The canyon is not just a crack. The thin sky is not just an emptiness. The crooked field is not just a problem child for a textbook. The rebel orbits are not just eccentric. Each is a way to point. We learned solar system order from circles on a page, from neat stacks of spheres, from the idea that exceptions are small noise around a strong song. The scar, the leak, the tilt, the sideways runner, each says the same thing. The map we learned is not the architecture that runs the place. We can answer in more than images. Cameras map what the eye cannot track at speed. Spectrometers pull signatures from light and turn them into lists of materials. Magnetometers sketch invisible scaffolds. Gravity itself becomes a tool, a way to weigh mountains and seas we cannot see. A small lander once fell gently onto a wandering stone, and the world watched dust behave like beads of glass. Up close, the rock told us two stories at once. One story is old and violent, of boulders and impacts. The other is delicate, of grains that move like snow only when the slightest nudge arrives, because the pull is a whisper. To put it another way, the closer we look, the more the familiar refuses to stay simple. A canyon that seems like a rip becomes a record of crust that cooled in waves. A sky that should fade into nothing becomes an archive of how stars erode their children. A field that should align with a tidy axis becomes a clue to a core that shifts or sloshes. The misfits do not orbit the truth. They are the spine that holds the book open. You can feel this lesson in your body. Step onto a high ridge in thin air, and every breath is a negotiation. Stand by a humming line, and know there is structure in space where your hand feels nothing. Watch snow turn to hard sculpture in slow wind, and understand that climate is a chisel. The solar system is not a museum of motionless spheres. It is a set of arguments carved in rock, ice, light, and field, and we have arrived in time to hear the middle of the debate. We will map the idea that Mars is not one world, but two histories welded. We will measure how air leaves molecule by molecule, and whether storms act as conveyors. We will test how a crooked magnet speaks about an interior we cannot touch. We will compare the sleep and fury of moons, where heat and brine may build engines that run for millions of years in darkness. We will follow the case for an unseen shepherd in the deep cold, and we will set that case against bias and small number tricks. At each station, we will ask what revision the misfit forces on the rule. If you stood inside the Martian canyon and looked up, stars would compete with noon. If you drifted over the tilted giant, auroral curtains would appear and vanish as if the sky were breathing. If you glided above a distant ice plain, shadows would look like mountains, then reveal themselves as spires carved by vapor, slow and relentless. Each sight is an instruction. Do not average this away. Do not flatten this into a neat diagram. Respect the detail. The detail is the code. What, then, is the big question? We will ask it as plainly as we can. Are these exceptions random scars? Or do they sketch the hidden architecture of our solar system? If it is an architecture, is it made of accidents only, or of patterns that repeat across scales, like the way a river branches or a crystal grows? If it repeats, what does it say about the odds that chemistry finds a stage and keeps it long enough to try complexity again and again? If the pattern is noise, then we will concede and call it so. If it is music, we will learn its key. There is a practical reason to care. Forecasting is a form of kindness. A system we can predict poorly is a system that surprises us with storms, with dust, with fields that flip. Lessons from a thin sky teach us how planets lose and keep what matters. Lessons from a crooked field teach us which technologies would ride out a storm and which would fold. Lessons from rebel orbits teach us how to plan for visitors that do not send postcards before they arrive. There is a human reason to care. We are meaning seekers, and meaning is slippery when we treat it as decoration. If we center the average, we miss the The hinge is where one state becomes another. The hinge is where time has leverage. In the solar system, the hinges are misfits that never quite sit down. They are more honest than the neat model, because they show their scars and their power at once. We must also be careful. Some teams propose that the outer clan of tilts points at a hidden giant. Others argue that our surveys looked in ways that favored a false signal. Both cannot be equally right. We will set up predictions that fail cleanly if the wrong story is told. We will resist the drift toward a great explanation that is easy to love. We will let the unsentimental part of the data lead. On the way, we will keep one promise. There will be only one guiding metaphor in each chapter, and it will not carry more weight than the instruments. A cracked atlas for Mars, a switch and a circuit for the tilted field, a blacksmith shop in a snowstorm for the moons that fight and feed each other, a compass that points sideways for the rebel orbits. Each metaphor will be a rung, not the ladder itself. The first act of our journey has to show the riddle, not solve it. Here is the riddle. The solar system we thought we knew keeps disobeying its own rules, and the pattern hiding in those disobediences may be the real map. If that line rings true, it will carry us through rock and ice, through fields and flows, through numbers and images, until the pattern either breaks or clarifies. If it breaks, we will say so. If it clarifies, we will draw it in chalk you can follow with your feet. You are invited to stand beside the canyon, under a sky that leaks light into noon. You are invited to float above a sideways world that blinks at the sun. You are invited to skim a plain where mountains grow from breath. Bring your questions. Bring your willingness to erase and redraw. Our reward will not be a single answer. Our reward will be a sharper way to ask what we are seeing. If this investigation speaks to you, like and subscribe to the Quiet Universe channel. The first planet we can study in real relief. Mars has been our mirror and our mistake. We once saw canals, then dust, then a dead place. Yet the instruments that orbit it now send home a stranger picture, a world divided against itself. The northern half is smooth, low, and young, a plain of floods and frozen mud. The southern half is ancient, battered, and high, a continent of scars. Between them lies a rough line that cuts the planet like an equator of trauma. Why should one body bear two faces, as if it had been two worlds welded together? Orbiters trace the line with lasers and radar. The difference in altitude between the hemispheres is not small. It is the height of Everest stacked on Everest again. Craters on the southern side speak of an old surface. The north shows few, a resurfacing that erased its memory. Some scientists read that contrast as evidence of a single massive impact, a blow that nearly unmade the planet and left a dent the size of an ocean basin. Others see signs of slow internal flows, mantle currents that reshaped the crust like dough rising unevenly. The truth may be both, a long war between heat and time. From above, the landscape shifts color as sunlight slides across it. Reddish dust drifts down from the highlands, coating the low plains in thin layers that move with each season. Here, a valley network snakes for thousands of kilometers. There, a chaotic terrain looks like collapsed ground, as if caverns below had drained. The more closely we look, the more every smooth area resolves into channels and fans, traces of running water that should not have existed so long under such a weak sun. If the air was ever thick enough to hold rivers, what happened to it? A visitor standing near the equator would see a sky the color of butterscotch and a horizon that fades into haze. The light is weak, 1/3 of what we know on Earth, yet the heat can still rise enough to lift dust miles high. Each year that dust grows into storms that spread around the world, a global tide that rolls across continents and hides the sun for weeks. When the storm passes, the surface is rearranged. Dunes shift, craters vanish, and the thin air becomes thinner still. It is as if the planet is sanding itself away, molecule by molecule. When the American and European probes took the first atmospheric readings, they found carbon dioxide, argon, and nitrogen in a fragile mix that would barely fill a small valley on Earth. Hydrogen and oxygen, the lighter gases, escape to space like fugitives. Every day, the solar wind peels off a few more atoms. A quiet theft measured in grams. Over billions of years, that trickle adds up to oceans lost. Not boiled away, but lifted, particle by particle, into the night. Mars is not dying. It is eroding upward. In plain terms, imagine trying to breathe while the wind carries away each exhale faster than you can draw the next. That is the reality for a planet with weak gravity and no magnetic shield. The solar wind flows past the world, finds no field to deflect it, and sweeps across the ionosphere like water over sand. Instruments aboard the MAVEN orbiter recorded plumes of charged particles escaping along invisible routes. The data draw a picture of air that does not fall but rises, an atmosphere that evaporates without heat. Why does this matter? Because the story of Mars is a manual for climate and habitability everywhere. It shows how distance from the sun, magnetic field strength, and geological activity cooperate or fail. A slightly thicker crust here, a slower rotation there, and the balance tips. On Earth, our core churns watts in enough to generate a field that wraps us in safety. On Mars, the dynamo froze, the field collapsed, and the atmosphere became a target. The difference between ocean and desert may be a matter of how long a planet keeps its heart molten. The low plains of the north still whisper of what was lost. Vast dried basins show patterns of ancient currents. Deltas where sediments pile in fans the size of countries. Rovers crossing those plains have found rounded pebbles and sulfate veins, minerals that only water can make. One rover once climbed from a clay floor into layers of rock where each inch marked a shift from wet to dry. It read the story of retreat, not of catastrophe, but of surrender. Even now, Mars breathes in small ways. Carbon dioxide freezes at the poles in winter and sublimates in spring, driving winds that carve streaks across dunes. Dust devils spin thin and fast, polishing the surface. Each season, the poles shrink and expand like lungs. Yet the air does not return to what it was. The pump leaks. The patient keeps breathing, but the breath escapes through invisible holes. We must also look at the mountains that rise from these plains. Olympus Mons, the largest volcano in the solar system, climbs 27 kilometers above its base. Its slopes are gentle, its rim broken. Its summit a cluster of calderas wide enough to swallow cities. The volcano's youth surprises us. Its last eruptions may have been recent in geological time, perhaps a few million years ago. Even a quiet Mars hides embers. If internal heat still moves, then perhaps the story of its halves is not over. Craters around the volcano show hints of frozen mud flows. They resemble glaciers, not lava, and they suggest that ice still lies beneath the dust, waiting for brief summers to creep outward. In the mid-latitudes, radar has found buried layers of ice thicker than any polar cap. The crust itself seems to sweat. For every place that looks dry, another hides frost a meter below. Water is not gone. It is disguised. Think of it like this. Mars is not a dead twin of Earth, but a frozen sibling caught midward. It began the same conversation about heat, air, and chemistry, then paused. We are reading a letter that stopped halfway through a sentence. The dust storms, the eroded valleys, the plains that echo with ancient deltas, all these are unfinished clauses. If life ever began here, it might have ended not in fire, but in forgetfulness, a gradual fading of the necessary layers. Why it matters again is simple. The frontier between the two hemispheres is not only a geological curiosity, it is a record of planetary fate. To understand why one side fell silent while the other resurfaced is to grasp how fragile habitability can be. We learn that energy and atmosphere are currencies, and that every planet pays for its balance differently. The price of stillness on Mars was the loss of protection. Each new mission adds a stanza. Orbiters read the minerals from light, landers taste the soil for traces of chemistry, and rovers measure isotopes that reveal how much gas escaped. The numbers converge on one truth: the planet once had enough air to keep water liquid for ages, then lost most of it slowly. There is no single villain. Impacts, weak magnetism, solar radiation, and internal cooling all shared the work. The result is the world we see now, sculpted by subtraction. Under a pale pink sky, a human could stand on a hill and see all four faces of Mars at once: the ancient highlands to the south, the smooth northern plains, the polar caps that breathe, and the volcano that remembers warmth. The scene would feel both huge and delicate, as if the planet were a clay model left to dry. Its quietness would not mean emptiness. It would mean patience beyond measure. Our first fracture mapped. We turn to the air itself, the breath a world could not keep. The thin sky of Mars is both veil and evidence. It glows faintly in ultraviolet, a gossamer halo that looks stable until you count what escapes. To the human eye, it is barely there. But to an orbiter's instruments, it is a moving current, a river of atoms leaving the planet for good. The mystery of how a world loses its air is not about one violent storm, but about time that never stopped working. Air is not only breathed or stored, it is negotiated with the star that warms the planet. When the first probes measured the upper layers, they found carbon dioxide breaking apart under sunlight. Ultraviolet photons strike a molecule, and it splits. Oxygen one way, carbon another. The lighter fragments have enough energy to drift upward, and once they reach the edge where gravity weakens, they simply do not come back. The sun does not need a dramatic explosion to strip an atmosphere, only steady pressure and patience. A few atoms per second per square meter, multiplied by the age of the solar system, is enough to erase oceans. Above the red plains, the solar wind flows like an invisible river of charged particles. On Earth, that wind meets a shield, a magnetic field that diverts it. Mars once had such protection. Its crust retains magnetic patches, frozen memories of a field that once wrapped the planet. But the field died when the planet's core cooled and the internal dynamo shut down. Without that barrier, the solar wind has free rein, a constant breeze strong enough to lift ions out to space. MAVEN, the orbiter that studies this process, recorded oxygen and carbon ions streaming away in long plumes like smoke from a slow fire. At its core, the loss is both mechanical and chemical. Charged particles hit the upper atmosphere and knock out electrons. Those collisions heat the gas, making it expand. The higher it swells, the easier it is for the solar wind to catch hold of it. Every flare from the sun delivers an extra gust, a temporary spike in escape rate. The math is brutal. When you plot the cumulative effect over billions of years, Mars ends up where it is today, with less than 1% of the air pressure of Earth. Simply put, a planet's ability to keep its air depends on three forces: gravity to hold it, magnetic fields to protect it, and internal heat to sustain both. Mars is smaller than Earth, so its gravity was already marginal. When the core cooled, the shield vanished. Once the shield vanished, the wind did the rest. It is a chain reaction of loss. If you could stand on Mars during a solar storm, you would not feel the wind on your skin, but you would see it in the flicker of auroras that dance near the equator instead of the poles. Charged particles follow crustal magnetic remnants, small arcs that trap and release energy like broken circuits. Each glow marks another leak, another exchange between the planet and the space around it. It is beautiful, and it is a symptom. Why does this matter? Because the same principles tell us what might happen to other worlds, and even to our own under extreme conditions. It shows how climate is not only surface temperature and clouds, but a dialogue between a planet's core and its star. When that dialogue ends, the sky begins to fade. Mars teaches us that habitability is not granted once, it must be maintained. There is another player in this slow theft dust. The fine grains that fill the air during global storms do more than shade the surface. They heat the atmosphere by absorbing sunlight, which lifts gases higher. Every major storm, like those in 2001 and 2018, acts as a temporary escalator for molecules trying to escape. Instruments recorded dramatic increases in hydrogen at the top of the atmosphere after each storm. The planet literally breathes harder during its dustiest days, and what leaves does not return. Rovers on the ground have watched the process begin in miniature. A whirl of sand rises from a valley, spinning into a dust devil that climbs hundreds of meters before fading. The air is too thin for true thunder, yet static charges build and discharge with crackling pops. Each tiny storm is a rehearsal for the global events that follow, a feedback loop between ground and sky. The more dust rises, the warmer the air becomes, and the more it can carry. To put it another way, Mars is losing air through both chemistry and weather. The carbon dioxide that dominates its atmosphere can freeze out at the poles in winter, forming seasonal caps that grow and shrink. When sunlight returns, the solid gas sublimates and rushes toward the equator, carrying traces of water vapor and dust. The cycle repeats each year, and each repetition shakes loose a little more of the high air. Over ages, those tremors add up. Imagine standing near the rim of Valles Marineris during a global storm. The sky turns brown, then orange, then nearly black as fine particles blot out the sun. The air temperature drops, then rises again from trapped heat. You would feel static crawl along your suit. In that darkness, the planet is reshaping its own weather from the top down. Above you, molecules are being pushed beyond escape velocity by forces you cannot see. Below you, sand grains skip and bounce, etching the next layer of history into the rock. Why it matters again is that this slow loss connects to the fate of water. Every molecule of H2O that rises can be broken by sunlight. Hydrogen, being light, escapes quickly. Oxygen lingers a little longer, combining with the surface to rust the soil. This is why Mars is red. Its color is not decoration. It is diagnosis. The planet's very hue tells us it has been oxidized by the air it could not keep. The more we study this balance, the more we understand that atmosphere is not a possession, but a balance sheet. The sun deposits energy. The planet spends it to hold on to air. The smaller and colder the planet, the worse the trade. Mars began with generous reserves. Volcanoes fed the sky with carbon dioxide, water vapor, and sulfur gases for hundreds of millions of years. When volcanic activity waned, the supply line broke. Without outgassing to replace what escaped, depletion was inevitable. Some researchers model alternate histories. If the planet had been slightly larger, the core might have stayed molten longer, sustaining a magnetic field. If the orbit had been closer to the sun, the added warmth might have triggered more volcanic recycling. Either change could have extended the breathable epoch by hundreds of millions of years. In those models, Mars might have kept seas, clouds, and perhaps life for longer than Earth has existed. But history is not rewritten by models. The world we have is the one that cooled too early. Think of this in human scale. A small campfire burns out faster than a large one. Once the embers fall below a threshold, the flames die even if there is wood left. A planet's core is the same. Without enough mass to trap heat, convection stops. The magnetic field flickers out, and the cold outer layers stiffen. The sky follows. When the heartbeat of the core stops, the breathing of the atmosphere slows, then fails. The loss of air also means loss of sound. On Mars, even a shout travels only a few meters. The thin gas cannot carry vibration well. A hammer strike makes no echo. The planet feels muted, as if wrapped in wool. That silence is another kind of data. It tells us that energy and communication both depend on medium. Without air, there is no voice, no weather, no shield, only radiation and dust. A lesson hides in that silence. Life, if it ever arose here, would have fought not only gravity and chemistry, but the collapse of its own sky. Microbes might have found refuge in rock pores or beneath ice, but the open world became hostile. The boundary between inside and outside grew lethal. To survive, life would have needed to reinvent home. Mars might still hold such enclaves underground, but the surface is a monument to surrender. Even so, the planet continues to teach. Each probe that measures isotopes, each radar that peeks beneath the surface, refines our sense of how climate and core are linked. We can see the fingerprints of solar storms in the isotopic ratios, the evidence that lighter gases escaped faster than heavy ones. We can see the tracks of past outgassing events, frozen in minerals that still contain trapped bubbles of ancient air. The story is not finished. The wind still writes the last lines. We are learning to read those lines not as failure, but as process. What Mars lost, it gave to space, and space will recycle it. Some of those molecules may one day drift into the tail of a comet, or into the thin exosphere of another world. In cosmic terms, nothing truly vanishes. It just moves up a level. Mars is an example of how energy redistributes, how the closed systems we imagine are never really closed. To lose air is not to die outright, but to change the kind of conversation a planet can have. Mars now speaks in dust and rock, in temperature gradients and ultraviolet glow. Its dialogue with the sun continues, quieter but still alive. The instruments that orbit and land are translators, capturing the faint sentences of ions that leave. If air can be stolen, what else can be switched? Perhaps an entire sky. Far beyond the red deserts of Mars lies a world that defies symmetry. Uranus rolls around the sun like a barrel, its poles aimed sideways at the stars, its equator nearly vertical to the plane of the solar system. In this tilted state, the planet seems to turn on its side and sleep through the seasons. Yet the real strangeness hides deeper, in the invisible cage of its magnetic field. That cage does not center on the planet's heart. It is off to one side, tilted at almost 60 degrees from the axis of spin, and it drifts as Uranus rotates. To an observer above the clouds, it is as if the planet's sky opens and closes in rhythm with a beat only the sun can hear. At first glance, the tilt seems absurd. Gravity, rotation, and magnetism should line up, at least roughly. They do for Earth, Jupiter, and even Neptune. But on Uranus, the field is a lopsided ghost, slashing through the atmosphere as the planet turns. Every 17 hours, the field's orientation with respect to the solar wind changes. When it aligns, charged particles pour in through the poles, lighting the upper atmosphere with auroras. When it misaligns, the flow is blocked, and the auroras vanish. The sky of Uranus is therefore not constant. It switches on and off, a cosmic lantern flickering in slow motion. Voyager 2, the only spacecraft to visit Uranus, recorded this dance in the 1980s. The data suggested a magnetic field that reconnected with the solar wind twice per rotation, opening and closing like a shutter. Later models confirmed that the planet's magnetosphere is among the most dynamic in the solar system. To understand it, we must picture not a simple dipole, but a tangle of invisible threads moving through a planet of ice and gas. The currents that sustain this field probably come from a shell of conducting water and ammonia under enormous pressure. There, fluid layers shift and twist, creating a generator that is both displaced and unstable. Simply put, Uranus is a magnet in motion, with its poles sliding through its own atmosphere. As it spins, the magnetic field lines sweep across space like a broken fan, alternately catching and missing the solar wind. The result is a planet whose upper sky breathes. Energy builds, releases, builds again. This breathing could have profound consequences for the chemistry of its atmosphere, for how particles move, and even for how the planet loses or gains heat from the sun. Why does this matter? Because it challenges our idea of how magnetic fields stabilize planets. We often imagine that a field is a simple shield, a static bubble that deflects radiation. Uranus proves otherwise. A field can be both protection and pathway, both wall and door. On Earth, magnetic storms are rare. On Uranus, they may be the weather. Every rotation changes what is exposed. There is no single north or south where particles enter. Instead, the zones of activity migrate across latitudes. Picture a lighthouse whose beam is not fixed, but wobbles unpredictably. Each time the beam passes, it bathes a different patch of sea. The sailors never know when it will return. That is Uranus, a lighthouse whose light is the storm itself. The auroral ovals that we map on Earth are steady crowns. On Uranus, they are elusive, transient bands that appear and fade with the rhythm of a spinning sky. The mechanism behind this is still debated. Some propose that the offset field arises from a layered core, with frozen water, rock, and metallic hydrogen arranged in unequal shells. Others suggest that the tilt began with a massive impact early in the planet's history, one so violent that it knocked Uranus onto its side and jumbled its internal structure. Both ideas agree on one point: the planet's interior must be asymmetrical. That asymmetry shapes everything above it. In plain terms, Uranus is a reminder that a planet's magnetic field is not a decoration. It is a window into the motions of matter deep below. If the field leans, the layers inside must be unbalanced. If it shifts, they must be restless. The magnetosphere is therefore a moving fingerprint of the planet's heart. By studying its fluctuations, we read the unseen. When solar particles strike the magnetic boundary, some are reflected, some captured. Those that slip through follow winding paths until they collide with atmospheric gases. The collisions excite molecules of hydrogen and methane, making them glow in ultraviolet. On Uranus, those lights flicker near the equator, a place where auroras should not exist. That alone tells us how far the rules bend. A sky that glows at its waist, not its poles, is a world turned inside out. What does this mean for climate? The switching magnetosphere likely modulates the flow of charged particles into the upper layers, altering how the atmosphere heats and cools. It may explain the planet's surprisingly bland appearance. Clouds of methane hide most features, and yet infrared instruments detect subtle thermal bands that shift with rotation. Energy from above could be shaping those patterns, imprinting the magnetic rhythm onto the weather. The deeper mystery is why Uranus radiates so little heat, unlike Jupiter and Saturn, which emit more energy than they receive. Uranus is nearly silent. Its internal furnace seems almost extinguished. Some think that whatever catastrophe tilted the planet also released its heat long ago, leaving a cold core that no longer convects strongly. If the dynamo layer floats above that cold heart, it could drift, creating the offset field we see. Thus, the planet's geometry may record the memory of trauma. Why it matters again is that Uranus and Neptune bracket a class of worlds we have only begun to understand. Dozens of exoplanets fall in their size range, intermediate between Earth and Jupiter. If we want to interpret those distant signals, we must decipher our own examples first. The sideways giant may hold the key to how magnetic fields evolve in ice-rich planets across the galaxy. From a human perspective, the idea of a sky that turns on and off feels uncanny. We are used to predictable days, to magnetic poles that wander slowly, not violently. On Uranus, compass needles would dance with every spin, navigation would be impossible, and radiation would come in pulses instead of steady doses. The planet redefines what it means to have weather. Think of the electric hum before a storm on Earth, the way hair lifts and skin prickles. That is a small echo of what the upper air of Uranus feels every few hours. When the field opens, the solar wind enters and compresses the ionosphere. When it closes, the pressure drops. The trapped particles spiral, and the sky goes dark. It is a breathing cycle written in magnetism instead of air. We can see the same physics in miniature around Earth during substorms. Satellites detect sudden releases of stored energy as field lines reconnect. On Uranus, such events are not local but global, sweeping across the planet's day and night sides in one rotation. The energy released is immense, enough to power the auroras and perhaps drive the chemistry that builds complex molecules from simpler ones. At its simplest, the switching sky teaches us humility. We build our models on the assumption of symmetry. Nature rewards imbalance, a field that drifts, a planet that leans, a circuit that opens and closes. These are not errors, they are variations of stability. The universe does not favor perfection, it favors persistence. The idea that a sky can switch also reaches inward. Our own magnetic field flips polarity every few 100,000 years. When that happens, the northern lights would appear in unfamiliar places, and navigation would have to adapt. Uranus compresses that cycle into hours. What we see there is an accelerated version of our own long-term heartbeat. If we could stand above the clouds and watch one full rotation, we would see the auroras brighten, fade, and return. We would feel no wind, only a slow pulsing of charged energy through the air. The light would be pale green and violet, shimmering across the horizon like curtains stirred by unseen hands. Beneath that light, a cold ocean of hydrogen and helium turns. Oblivious to the flicker above, the beauty would be calm, but it would never repeat the same way twice. A switch suggests a circuit, but life needs power and water. We go where stone hides seas. Jupiter dominates the solar system like a slow thunderhead, its gravity a net that gathers and disciplines. Yet around this giant spin 4 worlds that behave like a miniature solar family. Each moon carries a different story of heat and cold, of violence and stillness. Together they reveal that habitability is not only about distance from the sun, but about energy in motion. Where Jupiter pulls and flexes, chemistry answers. Where the pull eases, ice becomes archive. The closest of the 4, Io, is the Forge. Its surface glows with active volcanoes that paint yellow and orange scars across a world of sulfur frost. No other body outside the sun releases so much heat per square meter. The source is not internal radioactivity alone, but the tug of Jupiter and the resonance of neighboring moons. Io's orbit is not a perfect circle. Each revolution stretches and compresses the moon like dough, generating frictional heat within its interior. That heat melts rock, which rises in fountains hundreds of kilometers high. Spacecraft have seen these plumes burst into the dark, trailing bright arcs across Jupiter's shadow. If you stood on Io's surface, the horizon would shimmer with heat haze. The air would smell of sulfur if your lungs could stand it, though in truth, it is too thin to breathe. Mountains taller than Everest thrust up from plains of glassy lava. At night, which comes every 42 hours, the landscape glows faintly from molten rivers. This is not destruction, but exchange. Io sacrifices rock to stay alive, a perpetual engine of renewal driven by gravity's patience. Next outward lies Europa, the snow. Its surface is white, streaked with lines that look like cracks in old ice. Under that skin lies an ocean deeper than any on Earth, sealed by kilometers of frozen crust. Tidal heating from Jupiter and the neighboring moons keeps the ocean from freezing solid. The same flexing that tears Io's rocks apart gently kneads Europa's interior, turning potential into warmth. Plumes of water vapor have been spotted venting into space, brief breaths that hint at reservoirs below. In plain terms, Europa is a world with an ocean that never sees sunlight but still stirs. If the water is in contact with rock at the seafloor, chemical reactions could provide the same energy that supports deep ocean life on Earth. Hydrothermal vents here might substitute sulfur or ammonia for oxygen, creating ecosystems independent of the sun. The conditions are not a dream. They follow the rules of chemistry as we know them. If life can begin in such darkness, it will rewrite our sense of where life belongs. Why does this matter? Because Europa reminds us that warmth is not a gift from above, but a consequence of motion. A world can be far from its star and still host liquid water if it is caught in the right dance. The same gravitational music that punishes Io also sustains Europa. In this miniature system, destruction and potential coexist in orbit. Beyond Europa circles Ganymede, the largest moon in the solar system, bigger even than Mercury. Here, the forces reach a balance. The surface alternates between ancient dark terrain and bright grooved bands where the crust has stretched and frozen. Beneath lies a deep ocean, layered between ice shells and perhaps resting on a metallic core. What makes Ganymede unique is its magnetic field, the only moon known to have one. Generated by a liquid iron or saltwater dynamo, it interacts with Jupiter's massive magnetosphere, creating auroras that ripple across its poles. For scientists, that field is not only a curiosity but a clue. A moon that can forge its own magnetosphere must still be hot inside. Internal heat means geological activity, and activity means a chance for chemical diversity. Where Io shows us fire and Europa shows us ocean, Ganymede offers both in moderation. It is the midpoint, the experiment that managed stability. Farther out still is Callisto, a moon scarred and ancient. Its surface is the most cratered in the solar system, a record untouched for 4 billion years. Yet even here, radar hints at a buried ocean, sealed under a crust of ice 100 kilometers thick. Callisto receives less tidal stress than its siblings, so its interior is quiet. That quiet may be its strength. Radiation from Jupiter cannot easily reach the deep layers, making any hidden ocean calm and enduring. If microbes could survive there, they would live in a world of perpetual twilight, safe but isolated. Think of Jupiter's system as a furnace surrounded by snowfields. Io is the coal bed, hot and restless. Europa and Ganymede are the temperate zones, where heat meets water. Callisto is the frozen boundary, a library of what once was. The entire set shows how gravity sculpts possibility. The giant's pull stretches one moon into a volcano, another into an ocean, another into a magnet, and leaves the last as witness. To put it another way, life and geology are two versions of the same verb interaction. Where energy moves, structure evolves. Where it stops, surfaces turn static. Jupiter's moons prove that distance is a poor predictor of vitality. They are laboratories for how energy flows between rock and sky. Rovers have not yet touched them, but telescopes and flybys have mapped enough to reveal a mosaic of environments. We see sulfur dioxide frost glowing in ultraviolet, cracks on Europa that span thousands of kilometers, and magnetic auroras on Ganymede that sway as Jupiter's field passes. Each observation deepens the sense that the moons are not minor players but active worlds. Why it matters again is that these interactions offer a template for exoplanets. Many of the worlds we detect elsewhere circle giant planets close to their stars. Some may have moons large enough to mirror this configuration. If so, the dance of tides and heat could create habitats in places no sunlight reaches. Understanding the balance at Jupiter is therefore a rehearsal for reading alien systems. Human imagination naturally seeks stories of extremes, and here the extremes coexist within a few million kilometers. A world of fire touches one of ice, and between them, a moon holds its own magnet. They are proof that diversity arises from pressure, that beauty and chaos can be siblings. The contrast is not coincidence. It is the natural outcome of gravity carving order out of motion. Standing above Io's horizon, you would see Jupiter filling half the sky, banded and swirling, its lightning bolts flashing silently. From Europa, you would see the same giant hanging low, casting a reflection across an endless plain of ice. From Ganymede, the auroras would ripple green and blue above the night side, an alien echo of Earth's own poles. Each vantage point tells the same story. The power that binds them also gives them character. At its heart, this quartet of moons is a lesson in balance. The forge burns, the snow endures, and between them lies every shade of thermal life. Energy does not vanish, it travels. The heat Io gives up through volcanoes may even influence its neighbors through tidal feedbacks. Gravity is a quiet teacher, patient and consistent, shaping possibilities without preference. If oceans breathe beneath ice, what shakes the outer dark into strange orbits? At the edge of the solar system, where sunlight is as thin as smoke, small bodies wander in paths that should have been random. Most of them keep near the same plane, circling the sun like grains caught in a slow whirlpool. But a few do not obey. They tilt. They turn backward. They cut across the common lanes as if answering a private signal. One of these drifters was found in 2011 and given a simple name, Niku, meaning rebellious. Its orbit climbs high above the solar plane, loops behind the sun, and comes back down like a skipping stone. It is not alone. Several others trace similarly inclined routes, and their long axes seem to point in nearly the same direction. Coincidence? Or the whisper of a hidden mass pulling from afar? In any well-behaved system, small irregularities cancel each other, that they do not hear hints at a conspiracy of gravity. If an unseen planet lurks beyond Neptune, its slow tug would herd these distant objects into similar alignments. The idea is seductive, but also dangerous. Data are sparse, and the outer sky is large. Statistical patterns can mislead. The so-called Planet 9 hypothesis lives between signal and suggestion. It claims that a body 5 to 10 times the mass of Earth may orbit the Sun thousands of astronomical units away, taking 20,000 years to complete one revolution. Such a world would never have been visible to past surveys. Yet its gravity could write patterns across the debris we can see. The notion of a hidden giant is not new. Neptune itself was found through mathematical deduction, its position predicted from the wobble of Uranus before a telescope confirmed it. The logic seems to invite repetition. Look for what you cannot see by studying what refuses to behave. But the distances involved now are staggering. At the outer fringe, even a planet the size of Neptune would shine dimmer than a candle on the moon. Searching for it requires patient mapping of faint motion across years of photographs, a task that tests the endurance of both machines and minds. Simply put, a hidden giant would act like a shepherd. It would not dominate the light but the timing. Over millions of years, its gravity would tilt and cluster the orbits of smaller bodies. Their perihelia, the points where they come closest to the sun, would line up. Their planes would nod in rhythm. When astronomers plot these alignments, a pattern emerges that seems too neat to be random. Yet each new discovery can strengthen or weaken the case. Add one more object in a conflicting orientation and the order dissolves back into noise. Why does this matter? Because the question is not only about one planet, but about the shape of the solar system's history. If there is another giant far away, then the early system was even more violent than we thought. Planets may have been scattered like billiard balls, some ejected into interstellar space, one stranded on a vast oval orbit. That survivor could still haunt the deep night, unseen but not unfelt. If there is no such body, then the pattern in the data is a trick of small numbers, a mirror held up to our expectations. Either way, the pursuit exposes how we decide what counts as evidence. Imagine standing above the plane of the solar system, looking down at a slow spiral of ellipses. Most align neatly, like ripples in water. Then a few slash across them, tilted at steep angles. They are outliers, but their outlier nature repeats, which itself becomes a kind of order. The rebel orbits might be scars from ancient scattering events. When Jupiter and Saturn migrated early in the system's life, their combined gravity could have tossed countless objects outward. Some settled into tilted paths, caught between the sun's pull and the weak tugs of the known giants. These survivors are fossils of that migration. In plain terms, what we call Planet 9 may be less a new world than a label for our ignorance. The sky beyond Neptune is still a frontier mapped by hints. For every object we know, 100 hide in the dark. Telescope surveys have biases. They scan near the ecliptic, where most things should be. A tilted population could therefore appear clustered simply because we have not looked in the right places. Astronomers now plan deep surveys with wide fields to correct for this, and already the neat pattern shows some fraying. Science grows by such tests, by trying to break its own favorite toys. The speculation persists because it fits the habit of nature to repeat scales. Just as moons circle planets and planets circle stars, why should not smaller planets circle further still? The distribution of mass in the solar system hints at something missing, a gap between Neptune and the far belt of icy bodies. A hidden planet could bridge that gap, explaining why some orbits stretch so far yet remain stable. The math works, the numbers tease, but observation remains the judge. Why it matters again is that the idea tests our patience with uncertainty. The search for unseen influence is an old human instinct. We feel motion and imagine the mover. Sometimes that instinct reveals real structure, as with Neptune. Sometimes it leads to ghosts. Yet both outcomes refine the method. Even if no giant waits beyond Pluto, the act of looking will uncover thousands of smaller bodies, each a piece of the system's forgotten architecture. There is poetry in the possibility. A planet colder than any known, wrapped in frozen methane, dim as the background stars, drifting on a path so long that no civilization could watch it complete a single orbit. Such an object would see human history as a blink. Its seasons would last centuries. Its skies would be static. Its sun a distant ember. To find it would be to add one more verse to the song of imperfection that defines our planetary family. Think of traffic flowing one way, and a single car slicing across the lanes with friends behind. That is what these rebel objects are. Their shared defiance hints at a leader ahead, perhaps unseen around the next curve. If the leader exists, it will confirm that gravity sculpts from the shadows as well as from the light. If not, then we learn that chance and bias can masquerade as design. Both lessons deepen our humility. From a technical view, the evidence includes several clusters of trans-Neptunian objects whose orbital planes are inclined and whose arguments of perihelion coincide. Simulations show that an outer planet with a mass 5 times that of Earth and an eccentric orbit could maintain such clustering for billions of years. Other models, adding random initial conditions, can reproduce similar patterns without any extra planet. The verdict remains open, but the experiment continues. To put it another way, the search for Planet 9 is less about discovery and more about calibration. We are testing our instruments against the edge of darkness. Each time a new telescope captures a faint moving point, we update the map and the model. The hidden giant, real or not, forces us to sharpen our tools. That sharpening may be the real prize. The chase has a human rhythm too. Teams across the world compare archives, write code, and trade rumors of faint detections. Some nights, a pixel shift on a digital frame looks promising, then fades under scrutiny. Other times, a forgotten plate from decades ago provides the missing link to confirm an orbit. Patience becomes a kind of faith, though grounded in math rather than hope. Even the critics share in the wonder. They point out that the supposed alignments could result from observational bias, yet they still join the search. Skepticism here is not rejection, but participation. The sky is large enough to test every claim twice. What can we take from all this? That evidence is a spectrum, not a verdict. A hidden mass may indeed lurk out there, but until we see it, the best we can hold are patterns and probabilities. We live by inference long before we live by proof. The rebel orbits remind us that absence is as informative as presence. Each unexplained curve in a trajectory is a question mark written in motion. At night, when telescopes sweep the cold fringe, the data stream back with whispers of change. A tiny shift, a faint glint, a new dot against the stars. Whether or not that dot becomes a planet, it confirms the larger truth that the solar system is not closed. It is still in conversation with its past. The outer dark is not empty. It is a slow echo of formation still playing out. The hint of a hidden giant echoes elsewhere, and in places we dared to touch. It began with a whisper of radar from Earth, a tiny echo bouncing off a moving point of light. The point was an asteroid called Eros, a rock so small that a person could jump off its surface and drift away forever. To reach it was to chase a grain in a cosmic storm. Yet we sent a machine there, crossed millions of kilometers, and set it down gently on a world no wider than a city. When the probe named Near Shoemaker finally touched the surface in February 2001, it marked a turning point. For the first time, we did not just fly past a remnant of creation. We pressed our metal foot onto it. The place we landed is not a world in the ordinary sense. Eros has no air, no water, no color, but the tan of weathered stone. It spins once every 5 hours, its gravity weaker than a sigh. To stand there would be like standing inside a cathedral made of silence. The horizon curves almost at arm's length, and the sun burns with unfiltered light. A pebble kicked from the ground could become a satellite. The instruments aboard the probe registered a landing so soft that dust barely rose. The machine had arrived at a relic that has changed little since the solar system was young. These small bodies are time capsules, fragments of the raw material that built the planets. Unlike Earth or Mars, they have never melted or recycled their interiors. Their chemistry is primitive, and in that simplicity lies memory. The pebbles on Eros are older than continents, older than the moon's Maria, perhaps older than life itself. Each boulder records the slow rain of micrometeorites, each crater the record of collisions from before the planets found their paths. When sunlight hits their surface, it warms and cools without the buffer of an atmosphere, causing rocks to crack and shift. Even in stillness, change continues. Simply put, landing on a small asteroid is like reading the solar system's diary at its first page. The words are rough and incomplete, but they hold the rhythm of beginnings. By measuring the isotopes and minerals on Eros, scientists could compare them with meteorites that fall to Earth. The match was almost exact. We had, at last, touched the parent bodies of the stones that have been striking our planet for billions of years. The landing itself was improvised. The probe had not been designed to settle. Its mission was to orbit, map, and measure, not to rest. Yet as it ran out of fuel, engineers realized they could use the remaining thrust to descend slowly. The craft fell in stages, bouncing lightly before coming to rest on its side. Its cameras kept working for days, transmitting close-up images of a world made entirely of gravel and dust. In those images, we saw what a planet looks like before it becomes one. Why does this matter? Because every asteroid we visit fills a missing chapter in the story of how material becomes structure. The solar system did not assemble from perfect spheres but from rubble. Each piece collided, stuck, shattered, and merged again. Some grew large enough to melt and differentiate. Others, like Eros, remained in their primitive state, preserving a record of the chaos. By studying them, we can learn not only how the planets formed, but how they aged. In plain terms, Eros is a fossil of assembly. Its interior is riddled with voids, a honeycomb of stone and dust. When a shockwave passes through it, the energy scatters and dissipates. That makes such bodies surprisingly resilient. They do not shatter easily, they flex. Understanding that flexibility is crucial for future missions that might need to divert an asteroid. If one ever threatened Earth, pushing it gently would work better than trying to blast it apart. The first lesson of the Pebble was humility. Strength sometimes hides in looseness. Looking closer, we saw boulders piled on slopes steeper than friction should allow. Gravity there is so weak that pebbles barely settle. Some areas show hollows where debris seems to have slid uphill, an illusion created by uneven pull. The entire body rotates in a way that reshapes its surface every few thousand years. Nothing is permanent, not even on a rock that has no wind or rain. Time itself is the weather. Why it matters again is that these small worlds may have delivered the ingredients of life to Earth. Many contain water locked in minerals and complex organic compounds formed in the early nebula. When they collide with planets, they bring these materials with them. The same dust that coats Eros may once have seeded our own oceans. By landing on a pebble, we reached backward into the chemistry that made us possible. Think of the experience from the probe's perspective. It circled the asteroid for a year, measuring gravity by the faint pull on its orbit. It mapped every crater and ridge, each shadow shifting with the sun. When it descended, it carried the expectations of a species that had never touched such a place. The final moments were almost silent, a few radio tones, a gentle bump, and then images of alien pebbles under an alien sky. The lander was built by hands that would never touch its destination. Yet through it we extended our reach into a realm smaller than imagination. Landing on Eros taught us more than geology. It revealed that exploration scales both up and down. We dream of oceans under ice and of distant giants. Yet sometimes the most important step is onto something the size of a mountain. Each grain there contains a fraction of the whole solar system's story. To read it, we needed only patience, precision, and a willingness to aim at almost nothing. The success of NEAR inspired new missions. Japan's Hayabusa missions and NASA's OSIRIS-REx have since collected samples from other asteroids, proving that small worlds can be visited, studied, and even returned to Earth. The lineage of those missions traces back to that first quiet landing. Every later descent was easier because one team once dared to rest a spacecraft on a world that barely had gravity. Imagine being there, with the sun sharp as a white disk and stars unblinking in the black sky. The ground underfoot would feel like packed sand, the shadows ink dark. A single step would send you drifting. The quiet would be so complete that you could hear your own pulse through the suit. The realization would come slowly that you are standing on something that never knew erosion or sound, an untouched fragment of the original forge. We call Eros a pebble, but that is only from arrogance. To it, we are the dust. The encounter reminds us that exploration is not measured by size, but by precision. The smaller the object, the more exact the question we can ask. Each landing converts imagination into data, each data point into perspective. To put it another way, landing on a pebble changed how we think of frontiers. Space is not only vast, but detailed. Between the planets lie billions of stones, each a frozen page of history. We no longer see them as debris, we see them as witnesses. By touching one, we join the oldest conversation in the solar system, the one between gravity and time. The next chapter of that conversation will go deeper. Future missions plan to drill, to return samples, to listen for vibrations that reveal internal structure. The goal is not conquest, but understanding, to learn how matter behaves when gravity is almost gone. These studies will prepare us for everything from mining to defense. But more than that, they will remind us that knowledge often begins with a quiet landing. If a stone remembers, what does a dwarf world rewrite with climate and ice? Beyond the last true planets, sunlight fades into twilight, and the Kuiper Belt begins. Here orbit icy relics of the solar system's youth, fragments too small to clear their neighborhoods, yet large enough to carry their own climates. Among them is Pluto, once demoted, now restored in spirit as one of the most complex small worlds ever seen. When the New Horizons spacecraft flew past in 2015, it found not a dead rock but a living geography. There were glaciers of nitrogen, mountains made of water ice, and skies that changed color with the day. The images forced a question few had dared to ask. How could something so small behave like a planet? The first photograph of Pluto's heart-shaped plain became an instant icon. That region, called Sputnik Planitia, is a vast basin filled with frozen nitrogen. Its surface is not smooth but patterned into polygons, each tens of kilometers across. At their boundaries, ridges rise and drop, like seams between drifting ice plates. These shapes are not static. Over time, heat from below and cooling from above cause the nitrogen to convect. The ice literally flows. Where it sinks, cracks open. Where it rises, it smooths over the landscape. In this way, the heart of Pluto beats. Simply put, Pluto's surface is alive with motion even at 40 degrees above absolute zero. The energy comes not from sunlight but from internal warmth, the leftover heat of formation and the decay of radioactive elements in its rocky core. That heat, though feeble, is enough to keep the lower layers of nitrogen soft and mobile. It is also enough to support the possibility of a hidden ocean beneath the crust, an ocean that may still be liquid after billions of years of cold. When New Horizons crossed Pluto's shadow, it looked back at the faint atmosphere glowing blue in the backlight of the sun. The haze stretches hundreds of kilometers above the surface, made of particles so fine they scatter light like smoke. The atmosphere is mostly nitrogen, with traces of methane. It freezes out onto the surface in winter and evaporates in spring, migrating between hemispheres. Every orbit, the planet exhales and inhales its own air. Why does this matter? Because such cycles show that activity does not belong to giants alone. Pluto, though smaller than Earth's moon, still manages to recycle its gases and sculpt its surface. It shows that a body's vitality depends less on size and more on composition and energy balance. In its thin atmosphere and moving planes, we see echoes of the processes that shape larger worlds. The mountains of Pluto rise like frozen waves, some as high as the Rockies, made not of rock but of water ice hardened by cold into stone. They cast long shadows across the plains of nitrogen, marking a contrast between materials that should never coexist. Water, which flows so easily on Earth, here forms the scaffolding of the landscape. Nitrogen, a gas on Earth, plays the role of glacier. It is a reversal of roles, a chemistry of inversion that only deep cold can produce. To put it another way, Pluto is a world where the common becomes extraordinary. Air has turned to snow, rock to ice, color to shadow. The laws are the same, but the outcomes differ. Each layer of its surface tells of exchange between phases of matter. Sublimation carves pits, deposition builds spires, and beneath them, slow convection shapes the plains into cells that move like the bubbles in boiling water, except that each bubble rises once every million years. Looking closer at the poles, we find patterns of dark streaks and bright frost that change over time. They record Pluto's eccentric seasons. Because its orbit is elongated and its axis steeply tilted, sunlight varies dramatically across centuries. Sometimes one pole points toward the sun for decades, while the other lies in darkness. The result is a long climatic heartbeat. Nitrogen and methane migrate from one pole to the other, re-sculpting the surface every few centuries. In a single human lifetime, the change is invisible, but in geological time, the face of the planet renews itself again and again. Why it matters again is that Pluto's activity challenges the idea that the solar system's frontier is quiet. The edges are alive with slow processes. The heat that drives Pluto's glaciers may also sustain an ocean beneath its crust. Models suggest a layer of liquid water sandwiched between rock below and ice above, kept unfrozen by pressure and trace amounts of ammonia. If that ocean exists, it has been sealed away since the early days of the solar system, perhaps preserving the chemistry of its birth. Imagine standing on the edge of Sputnik Planitia. The sun would be a small white spark in a dark blue sky. The horizon would shine with a faint haze, and the air would be so thin that frost would form on your suit, beneath your boots. The ice would creak slowly as it flows, a glacier made of molecules that are gas on Earth. Distant mountains would glimmer, their peaks made of water ice that gleams like marble. Every few moments, a grain of nitrogen snow would drift down, silent and dry. In that silence, the idea of emptiness would vanish. There is nothing dead about such stillness. It is the sound of time stretched thin. The tall spikes seen near Pluto's equator, called penitentes, rise hundreds of meters high. They are formed when sunlight sublimates nitrogen and methane ice unevenly, leaving behind sharp ridges. Similar structures exist on Earth in high Andean deserts, but on Pluto they reach the scale of skyscrapers. These mountains of breath, sculpted by the faintest heat, remind us that even the weakest energy can do enormous work given enough patience. In plain language, what we see on Pluto is the triumph of subtle forces. Radiation that could barely warm a fingertip moves continents of ice. Gravity, a fraction of Earth's, molds mountains that last for eons. Change comes not in bursts, but in whispers. This slow architecture may be the most honest version of planetary life, one that values persistence over drama. There are other dwarfs out here too, each with its own oddities. Eris reflects more light than fresh snow and may host an even thinner atmosphere that freezes solid in winter. Haumea spins so fast it has become an elongated ellipsoid, flinging fragments into its own orbit. Make glows red with complex organics that coat its surface. Together they form an archipelago of enigmas, small worlds that refuse to vanish. Each carries traces of what the early solar system kept and what it lost. Why does it matter beyond curiosity? Because these worlds remind us that exploration is not about scale, but about surprise. The lesson of Pluto is that even at the boundary, processes continue. Energy and matter still converse. If planets are stories, Pluto is a chapter that rewrites the ending. It shows that the frontier of our system is not a static graveyard, but a laboratory where heat, ice, and sunlight still negotiate. When New Horizons left Pluto behind, it turned its camera back for one last look. Against the dim glow of the sun, the planet's thin atmosphere formed a halo of blue. It looked like a gemstone suspended in darkness. That image carried more than beauty. It carried continuity. The same physics that shape Pluto's haze also shape our own sky. The connections stretched across billions of kilometers, linking the edge to the center. If we ever return, it will be to learn how such delicacy persists. What mechanisms keep a heart of ice beating so far from the sun? What stories lie beneath the frozen nitrogen sea? Each question opens another layer of wonder. Imagine frost carving cathedrals taller than skyscrapers where noon is twilight. The pattern is no accident. And Act 3 will ask what it asks of us. Across the 7 worlds we have visited, from the canyons of Mars to the frozen plains of Pluto, one truth keeps surfacing. The solar system is not a collection of separate bodies, but a single experiment in endurance. Each planet, moon, and fragment performs a version of the same theme, energy-seeking form resisting loss, loss turning into pattern. The hidden architecture is not a plan drawn by intent, but a rhythm carved by consequence. What we call laws are simply the habits of matter repeated until they become music. Stand back and the pattern resolves. The inner planets burn their memory into rock. The outer ones hide theirs in ice. Between them, gravity stretches invisible strings. Each oscillation of field and motion becomes a verse in the long poem of structure. Mars keeps its canyon as testimony to absence. Jupiter keeps its moons as proof that contrast can coexist. Uranus turns sideways, showing that even imbalance has geometry. Pluto drifts in twilight, still sculpting its breath into mountains. The message is not stability, but resilience. When we looked for order, we found exceptions. When we examined exceptions, we found continuity. That reversal may be the real discovery. The solar system teaches by paradox the crooked magnetic field that still protects, the dead volcano that preserves its heat in silence, the frozen world that recycles its air. Perfection here is not a circle. It is a spiral. Every orbit is a promise to return changed. Simply put, the cosmos keeps its structure through motion, not stillness. Change is the equilibrium. The more energy a world loses, the more elegantly it adapts to keep something alive. A canyon deepens, an atmosphere thins, a crust bends, a magnetic field stumbles into new orientation. Nothing holds, yet everything persists. If there is design, it is the patience of physics. Why does this matter? Because we are not outside that pattern. Our planet is one more variation of the same rule. a body learning to balance heat, magnetism, and time. The faint breath of Mars leaving its sky warns us what happens when balance fades. The flicker of Uranus reminds us that instability can still be beautiful. The ice of Europa and Pluto tells us that stillness can be fertile. The lesson is not caution alone, but continuity. We belong to a system that improvises. In the beginning, Earth too was chaos, a molten echo of Eo's furnace. It cooled, fractured, and found its own quiet. Life rose, not as an interruption, but as another expression of feedback. Every heartbeat, every breath, mirrors the same oscillation between energy and loss that shapes planets. Our magnetosphere hums with the same physics that lights the auroras of Ganymede. We are the local manifestation of a cosmic reflex, the urge to maintain difference in a field that seeks equilibrium. At its core, existence might be defined as resistance to evenness. A canyon resists the flat plane. A charged particle resists the void. Consciousness resists forgetting. The structure we see in the solar system is the record of that resistance. Yet it is not defiance for its own sake. It is creative. When a world tilts, it invents new climates. When an orbit shifts, it opens room for moons. When a magnet bends, it invites new light, even ruin builds. To put it another way, the solar system is a slow conversation about memory. Rocks remember pressure. Fields remember motion. Ice remembers sunlight in layers of blue. Every observation we make is an act of listening to that memory. Each measurement is translation from the language of gravity to the language of thought. The process makes us participants, not spectators. Consider how far our instruments have carried us. We have watched a planet bleed its air into space, seen oceans hidden under ice, felt the pull of mass we cannot yet name. Our machines, drifting in silence, have become our eyes where our bodies cannot go. Yet the most profound discovery they deliver is humility. The closer we look, the less we can treat ourselves as separate. The same forces that shape dust into worlds shape neurons into questions. Why it matters again is that this recognition changes how we think about exploration. The search for life elsewhere becomes a search for continuity, not novelty. Finding microbes under Europa's crust or in the dark ocean of Enceladus would not diminish life on Earth. It would confirm that the pattern extends beyond us. Life would cease to be a local accident and become a cosmic habit. We are not the first to map from absence. Every planet before us has done so, carving knowledge from constraint. Mars teaches the patience of loss. Europa, the virtue of secrecy. Uranus, the wisdom of tilt. Pluto, the strength of silence. Each world holds a mirror to a human condition, breath that can fade, energy that can wander, warmth that must be protected. The more alien we look, the more familiar the reflection becomes. Think of the metaphor that began this journey, the watchtower. We stand at its top now, looking outward and inward at once. The view is immense, yet the silence is not emptiness. It is a field of potential waiting to be read. Every star is another library, every planet a page. The hidden architecture we chase through dust and ice turns out to be the same structure that shapes thought patterns sustained by difference. At this height, even time seems to thin. The scale of billions of years collapses into one long exhale of the cosmos. Mountains rise like frozen waves. Magnetic fields shimmer like breathing. Atmospheres bloom and fade like slow tides. The story has no proper ending because the rhythm continues. We are living inside a sentence, still being written. We might ask, then, what this architecture demands of us. Observation is one answer, stewardship another. If the same physics that makes Pluto's heartbeat also warms our climate, we have to treat balance as sacred. Every measurement, every exploration carries responsibility. The more we understand, the more we are woven into what we study. Knowledge and care are not separate tasks. In the final light, When we look back across the system, we see a tapestry of contradictions resolved into coherence. The hot and the cold, the tilted and the level, the bright and the dim, all share one rule: persistence. It is the quiet virtue of the universe, the one that outlasts brilliance. Our own survival may depend on learning that rhythm deeply enough to join it. The philosopher once said that we learn not from what obeys, but from what refuses. The solar system is the grand refusal, the collective insistence that imperfection be allowed to work. Out of that permission comes complexity, and from complexity, awareness. If we listen long enough, even the silence speaks. Now the question remains, simple and enormous if meaning hides in the exceptions. What exception are we to our own cosmic rule?